I'm really glad to be there in Lumini, and I will present you a joint work with Fabrice Baudouin, which is in Connecticut. And in fact, most of my talk will be about fractional Gaussian fields on fractal. And if I have time, I will give you an extension to the stable framework. Okay? And so, quickly, the outline of this talk. In the first part, we will focus on a classical field, which is the fractional Gaussian motion, which is not defined on fractal, but on Rn. Okay? And so, listening to Nassas and Guillaume, I decide that no one knows what is a Gaussian field, and so I begin with the definition of a Gaussian field. And the most important things for me would be the link there exists between fractional Gaussian motion on Rn and the fractional Laplace operator. Why is it important for me? Because we will introduce the fractional fields indexed by Sierpinski-Gasket exactly as you can define fractional Gaussian motion owing the Laplace operator. Okay? Then in the second part, I will do as if you don't know Sierpinski-Gasket, and so I introduce the Sierpinski-Gasket and the tools I need on it, and especially what is the fractional Laplace operator on Sierpinski-Gasket. Okay? And the last part will be about fractional fields indexed by the Sierpinski-Gasket. I must say that Sierpinski-Gasket is just an example for the talk, but you can deal with other fractals, but that's simpler to present on an example what we can do. So I'd wait for you. So fractional Gaussian motion is a Gaussian field, so maybe for some of you it's a recall, but when you consider a Gaussian field, that means that you consider a collection X of random variable. So a collection because there is this index X, which lives in a non-empty set U, and a random variable because there is a second variable W. So you can see it or as a function of X, or as a function of W, or as a function of X and W. And you say that this collection is a Gaussian random field if any linear combination of the random variable X of X that you can construct, you can build, is a Gaussian random variable. That's great for everyone? Huh? So such a random field, in fact, is characterized by only two deterministic functions. I mean, characterized in a distribution. So its distribution, if you assume that it is Gaussian, will be characterized by its mean function, mx, which is so the function which to x assign the mean of x of x, and the covariance function between x of x and x of y. In all the talk, I will only consider centered Gaussian fields. So that means that for me, now m of x is always equal to 0. So when I give the covariance, it disappears. Okay? And the last thing which is important is that I will be interested in the sample path smoothness of the fields I study. And when the field is Gaussian, it can be linked to the behavior of the variance of its increments. So you take an increment and you take its variance. Okay, you can express it using the covariance function. And if you know of this variant, the behavior of this variance, you can have an idea of the sample path smoothness. What means sample path smoothness? That means that I look at x for a fixed omega, and I look at it as a function of the index x. Okay? So now I can introduce fractional Gaussian motion on Rn. So the set U will be Rn mx will be equal to 0, so I need to give you what is the covariance function. So the covariance function of the fractional Gaussian motion, so the fractional Gaussian motion, usually we denote it by BH, okay, where H is an index between 0 and 1, and so it is the center Gaussian random field whose covariance is given by this. So the covariance is controlled by the index H. And in fact, the index H also controls the sample path smoothness. So you got there an example when n is equal to 1. And what you can see is that the greater H is, the smoother are the trajectories, are the sample path. Okay for you? Okay, so H is called in practice the Hurst index of BH. And so I explained that the sample path smoothness is a consequence of the behavior of the variance of an increment, and for fractional Gaussian motion, it is quite easy to see that the variance of an increment only depends on the distance between x and y, and it is this distance to the power 2 times h. And from this, you can deduce that up to change a little bh, you can give a control of its increments. What do I mean by up to change bh? That means that I can find a new random field bh star, but bh star at point x is more or less bh at point s, because it is almost surely equal to bh of x. Okay? And so up to change on negligible set bh, you will see that BH star has continuous sample path. You can even prove this result. We say that we give an upper bound for the modulus of continuity of BH star. And the first consequence, one immediate consequence, is that the BH star has locally Eulerian sample path. Of order gamma, as soon as gamma is strictly less than h. And in fact, it is an optimal result. You can prove also that BH star doesn't have locally Eulerian sample path of order gamma as soon as gamma is bigger than h. Okay? So really h, as you have seen there, controls the sample path smoothness. Nice for everyone? Okay. So why do I give you this result about fractional Gaussian motion? Because we will be interested in proving exactly the same results for the fractional fields on Sierpinski gasket. So at the end of the talk, you will see exactly the same thing, but BH will be replaced by the fractional fields on Sierpinski gasket. Not exactly the same, because we don't have the optimality. Okay, so now to finish about fractional Gaussian motion, what is the link with fractional Laplacian? So I need two tools before. I need to say what is a random measure and what is a stochastic integral with respect to this random measure. So I will consider W a Gaussian random measure with intensity mu, where mu is a sigma finite measure. Okay. E will be Rn for our example, but I take any E because then E will be the Sierpinski gasket in the following of the talk. So the first property there corresponds to the sigma additivity of the measure. So the measure of an union, as soon as your set there are pairwise disjoint, is the sum of the measure of each set almost surely. Okay. Then there is a property, we say that the measure is independently scattered, so that means that if you take pairwise disjoint set, the measure of each set will be a random variable, and all these variables are independent. Okay. And last property, that's just to explain why I say it is Gaussian. Why I say with intensity mu. So the last property explains these two words. W of a set A is simply a Gaussian variable. She will be centered, and its variance will be the mass mu of A. If you have questions, don't hesitate. Right? So once you have this, you can define a stochastic integral with respect to W. So I won't explain how you build the integral. I will just give you the properties that will allow you to understand the meaning of the stochastic integral. So you can define, if you take W, the Gaussian random measure with intensity mu, you can define the stochastic integral of f with respect to W as soon as f is square integrable. Okay. And in fact, W of f will give you an isometry from L2 of E to L2 of omega. So the random variable which have a moment of order 2. And so this stochastic integral still be a Gaussian variable. It still have a mean equal to 0. And so, as you may know, Gaussian variables are characterized by their mean and their variance. So what you need to know is the variance of the stochastic integral. And the variance is nothing else than that's the square norm of f with respect to the control measure mu. Okay? So now I have the random measure, I have the stochastic integral, and on Rn, I think that everyone knows what is the Laplacian, so I can give you the link between the fractional Gaussian motion on Rn and the Laplace operator. So this follows from a survey of Lodia, Sheffield, Sun, and Watson. So they consider W a random measure on Rn. So E is equal to Rn. The control measure mu is, in fact, here the Lebesgue measure on Rn. And then you introduce the Laplace operator delta. And for any parameter S, which is a non-negative, you define the fractional Gaussian field X indexed by S as the fractional operator here of order S applied to W. So, this, okay, looking at that, what does that mean? In fact, you should understand this in terms of distribution. So that means that X of S applied to a function f, where f is in the Schwartz space, is a stochastic integral, and it is the stochastic integral of f. You apply the Laplace operator of order S to f, and then you integrate this function with respect to W. Okay? The link with fractional Gaussian motion. We don't see it. There is no fractional Gaussian motion in this definition. So in fact, for several values of S, you can interpret X of S. For S equal to 0, that's nothing that white noise. For S between n over 4, where n is the dimension of Rn, and n over 4 plus 1/2, you can prove that, in fact, S applied to f, you can have another representation, and you can write it as the integral of f times bh, where bh is a fractional Gaussian motion. So I need to link h and s, and h and s are linked by this equation. So have a look on the range there for s, and you will see that this will describe 0, 1. Okay? So we say that BH can be understood as the density of the fractional fields X with respect to the Lebesgue measure. Is there some question? No? So in the following, I will exactly take this definition. I will, of course, don't take a measure on Rn. I will change to have a measure on the Sierpinski gasket. I won't take the Lebesgue measure. I will take what we call Hausdorff measure on the Sierpinski gasket. And I will define my fractional Gaussian field by this equation that should be understood by this. Okay? So I take K a fractal set, I take a measure on K, and my fractional Gaussian field on K is the Laplace operator of order S applied to W, where W is a Gaussian random measure with intensity mu. And so, as I say, I only deal with an example. So my example is K, the Sierpinski gasket. I need also a metric, and it will be the Euclidean metric. And I need the Hausdorff measure formula. That's not, you need several tools there that maybe you know, maybe you don't know. So what is the Laplace operator? How do I define the fractional Laplace operator of order S? And what is the Hausdorff measure on the Sierpinski gasket? That's the aim of the second part of the talk. So Sierpinski gasket and fractional Laplace operator. I take the triangle with vertices 0, 1, and Q3, with length equal to 1, and I need some contraction map there. So if you apply F1 to this triangle, you will obtain the smaller triangle there, which is red. If you apply F2, you will apply the green. You will obtain, the green triangle. And if you apply F3, you will obtain the pink triangle. And to define the Sierpinski gasket, you apply and apply and apply by induction the map, the contraction map, and you will have a convergence, and you will obtain this, which is called the Sierpinski gasket. There is another way to define the Sierpinski gasket. You can also say that it is the unique non-empty compact set that can be recovered if you apply F1, F2, and F3 to itself and take the union. That's the only compact set which satisfies this. Great for you? So you've got the triangle, the Sierpinski triangle. Now you need the Hausdorff measure. So what is the Hausdorff measure? So the Hausdorff measure will be a probability defined on Borel's set, and she's characterized by this. So you apply n times the contraction. Each time you choose F1, F2, or F3, and you apply n times these contractions to K, and you say that the mass of this set will be 1 over 3 to the power n. Okay, if I apply one contraction. If I apply just the F1, I obtain the smaller Sierpinski gasket, and there is self-similarity properties there, and so you can say that it is a Sierpinski gasket, but smaller. And the mass of this Sierpinski gasket is 1 over 3. If you apply F2, you obtain the green one, and you say that the mass is 1 over 3. And if you apply F3, you obtain the pink one, and it will be also of mass 1 over 3. If you say now that you take n equal to 2, so you apply 2 contraction, you will obtain one of the triangle I put in, which are in red, green, or pink there. So they are again smaller. And you say that their mass is 1 over 9. Okay? If you apply 3 contraction, you will obtain more triangle. They will be smaller, and their mass will be 1 over 3 to the power n. Each time you apply a contraction, you divide the mass by 3. Okay? And there is a unique measure that satisfies this. It will be a probability, and it is called the Hausdorff measure. So one property, I think that we have seen it in several talks. I list two. One key property for for the study we have done is that this measure is alpha regular. Okay. So that means that when I say you can apply to any fractal, you must have chosen a measure mu which is alpha regular if you want to have the same result. So the measure there is alpha regular. That means that the mass of a ball of radius r is, in some sense, of the order r to the power dh. And here dh is the Hausdorff dimension of your Sierpinski gasket. So this Hausdorff dimension is known as ln of 3 over ln of 2. Okay? So the mass of a ball is of the same size of the radius r to the power dh. And that will be important, and you will see that in the sample path smoothness, dh will appear. Okay? Okay, so I have the Sierpinski gasket, I have the Hausdorff measure. I give you one key property of this Hausdorff measure, and now I need the Laplace operator. So the Laplace operator, I will define some Dirichlet form. So first, I consider the vertices of the Sierpinski gasket. So it is Q1, Q2, and Q3. And I define this form, where here in the sum, Vy is just you have applied n times the contraction. Okay? So you only consider here the edge of your Sierpinski gasket. Okay? When you apply, for example, n equal to 1 in this sum, so you will, for example, have this Sierpinski gasket. If you choose to apply F1, you take all the edge of this Sierpinski gasket, you make the square difference of the function between these two edges, and you sum over the free triangle. Okay? If you decide to look at the form when n is equal to 2, you will have 9 triangles, so here there is 9 sum. And for each triangle, you look at the square difference between the distance between the function f at 2 edges of the triangle. Right for you? Okay, that defines a quadratic form that's also an increasing sequence, so you can let n go to infinity and say, okay, I will set the quadratic form E as the limit of this sequence. Okay. You don't want to have plus infinity, so you only consider the function f such that the limit is finite. So now there is some result in Kigami. So Kigami, there is a book, Analysis on Fractal, where you can have a lot of things. And so you can see in this book, for example, that the quadratic form equipped with this set F will be what we call the local regular Dirichlet form on L2. And when you've got a local Dirichlet form, there is an operator associated to this local Dirichlet form that I denote by delta there. And we call this operator the Laplace operator. And in fact, here in this talk, it is the Neumann Laplace operator because I don't want to have some boundary condition. Okay, so this is the Neumann operator. You can define several Laplace operator, but you need to say what are the conditions on the boundary. Okay, so that's just the Laplace operator. Now I need to define the fractional Laplace operator. So to define the fractional Laplace operator, I will introduce an orthonormal basis of eigenvalues, of eigenfunction, of the Laplace operator. So I consider the square integrable function with mean equal to 0, and then again you can have a look on a Kigami book. You will see that there exists a sequence of eigenvalues that you can range for minus delta. We take minus delta in order to have a positive eigenvalues, and you can find an orthonormal basis. So phi j is an eigenfunction for the eigenvalues lambda j. Okay, minus lambda j. Okay, then that means that if I take if you choose f in square integrable, you can now give its decomposition in this orthonormal basis. So you will say that it is the sum of the scalar products of phi j and f times phi j. Okay, and you sum for j equal to 1 plus infinity. Right? So now, if you apply the operator, more or less the definition which is there comes from what I will write. You will say that, okay, that means that I will take the same sum, I take the scalar product, and then I apply the operator to phi j. And so I need to define what is the operator, the fractional Laplace operator to phi j. And so if you have a look at the definition, you say, okay, Laplace operator applied to phi j is minus lambda j applied to phi j. So phi j, if you take minus 1, you will say okay, if you apply s times, s doesn't need to be an integer, but that's the idea. Okay, and then you put this inside of this, and you obtain the formula which is on the slide. And so you can check that. Can I switch off the light? Yeah? I know what to do. Okay. So now you can check that this gives you a series which converges, and the function you obtain will be a square integrable function, and its mean will be equal to 0. Okay? So you've got now the Sierpinski gasket, the measure, and the Laplace operator. So I can define my random film. Just if it was so simple, it was not on in the outline, but I need another tools, and the other tool is about the it kernel. Okay. I need to introduce the it kernel so that I can compute everything for my fields, and I need to introduce you another number which is called the bulk dimension. So you've got your Dirichlet form. You know that its generator is delta. When you've got a generator, you can associate a semigroup, Petit, of a Markov process. And here, this semigroup will have a it kernel. That means that PTF will be an integral operator, and its kernel is PTXY, whose name is the heat kernel. Okay? And there is some result about Barlow and Perkins who proves that the behavior of Petit of X is of this kind. By this symbol, I mean that you can find a constant and give an upper bound of Petit, which is a constant times this. You can find another constant and say that the lower bound for Petit is this times this smaller constant. Okay? This is only true when it is between 0 and 1, when you consider the Neumann operator. And here, so there is the Hausdorff dimension, but there is a new parameter dw, and dw is called the Walk dimension. And we know its value, you got there. So this estimate is called sub-Gaussian just because dw is bigger than 2. No question? Okay, so at the end of the talk, I will give you the sample path smoothness, and there will be 2 parameters which are of interest, dw and dh. And of course, the order S of the Laplace operator. So, fractional Gaussian fields on Sierpinski gasket. More or less, I will take the definition I give you from Lodia and al. And just replace with the new variable I introduced in the second part. So, for the moment, forget this. So you say that the fractional Gaussian field XS is the Laplace operator of order S applied to W, where W is your Gaussian random measure on your Sierpinski gasket. So we have proved that if S is in this interval, and I will explain you this bond, there exists a density for these fractional Gaussian fields, so X tilde. So that means that my fractional field XS applied to F is in fact the integral of F times X tilde with respect to the Hausdorff measure mu. Okay, so that's exactly what was written for fractional Brownian motion, but for fractional Brownian motion, K was Rn, and mu was the Lebesgue measure. Okay, and we have also that X tilde has a smooth sample path up to a modification, so up to change it a little, like I have done for fractional Brownian motion. You can consider that it has older sample path. I don't need locally because I am on a compact set, so locally is not is the same. Of any order gamma, as soon as gamma is strictly less than this. So you see dw, the Walk dimension, dh, the Hausdorff dimension of K, and the order of the Laplace operator S. Okay, so this ensures that this parameter is between 0 and dw minus dh. Now, this implies that h is between 0 and dw minus dh. Okay, so you can say what happens if S is less than this bond? What happens if S is bigger than this bond? So if S is less than this bond, in fact, there is no density. So since there is no density, I cannot study the sample path smoothness, so I'm not interested in for this paper. If S is bigger than this, we didn't do it in our paper, but in fact, there is also some work of Fabrice and Chen. They don't consider the Neumann Laplacian, they consider the Dirichlet one. So they had a boundary, a condition on the boundary, and they prove for Dirichlet Laplacian that there still exists a density when S is bigger than this. Okay, you follow exactly the same proof, and you see that for us, you still have a density when S is bigger than this upper bound. So the difference is that on the parameter h there. Whatever S you will choose, you will find exactly the same order of sample path smoothness. So that's a kind of critical exponent. After this exponent, you will be, in fact, Eulerian of order dw minus dh, and that's all. Okay? Whatever S is. So, okay, we did not consider it, but as I say, have a look on these two references, and you will see that it still works. So, just some idea of the proof, just what is, not really the idea, but what is X tilde? Because if I want to study its sample path, I need to know a little what is it. So, in fact, to define X tilde, first we introduce the fractional with kernel. So the fractional with kernel is linked to the it kernel, and it's in the case of Neumann Laplacian, it is defined by this equation. And you can prove that GS is square integrable when S is larger than dH over 2 times dW, my lower bound, in fact. If S is less, G square is not in L2, and so I cannot define then my stochastic integral. Okay? And you can introduce an integral operator. So GS applied to F, whose kernel is this very kernel. Surprising or not, this operator is nothing else than the Laplace operator of order S. So you can prove that this operator is in fact the fractional Laplace operator of order S applied to F. Okay, almost everywhere. For almost X with respect to the Hausdorff measure, this function is equal to the Laplace operator of order S applied to F. And so then with this relation, you can prove that in fact, okay, there is a density, and this density is nothing else than the stochastic integral of your with kernel with respect to your Gaussian random measure. Okay, so the proof to verify that this is the density is based on this equation. Okay. So now I have the density. I want to study its sample path smoothness. I know it is a Gaussian field, and I said at the beginning that the sample path smoothness of a Gaussian field is linked to the behavior of the variance of its increments. So I want to consider an increment and try to compute its variance and try to say, okay, the behavior of this variance is this. So I know what is the smoothness. So to do so, I know how to do this. The behavior we have there, we have the behavior, in fact, of the integral operator. As soon as S is less than this lower bound, and by duality, you, since GS is the kernel of this operator, you can obtain the behavior of this integral. And this integral, if you remember the property of the stochastic integral with respect to a random measure, is nothing else than the variance of the increment I'm looking for. So from this, using duality, I can prove that this integral is less than this. And it is well known, using some entropy method, that when you have this kind of behavior, you can obtain some result about the smoothness. Okay? And so that's the aim of the following slide. So what you obtain using classical entropy method, you obtain an upper bound of your modulus of continuity. That's exactly the same, except that H now is the S, this parameter, That's the one I stated before for fractional Gaussian motion. Okay? So up to change a little x tilde, you know that x tilde satisfies this, and from this, you obtain, of course, that your sample paths are locally Eulerian of order gamma as soon as gamma is strictly less than h. Okay? I don't know if it is optimal. We think so, but we don't succeed to prove it. What we need to prove this for fractional Gaussian motion, if you remember, we have obtained an equality. We have obtained for fractional Gaussian motion, the variance is equal to the distance to the power 2h. Here I have only an upper bound for this variance. If I want to prove that my result is optimal, I need that one way to do it is to have a lower bound. If I succeed to prove that this is also bigger than a constant and the same distance and the same power, I can conclude that the result is optimal. If I don't succeed, I cannot. So we didn't succeed, so that's an open question. Okay, so I have time, a little. So just about the generalization, if you don't want to do more than Sierpinski gasket. So you need to take for K what is called the fractional metric space in the sense of Barlow. So that means that K will be a compact metric space that you can embed in an Euclidean space with an isometry. That means that for mu, you will also take the Hausdorff measure, so some kind of measure defined like I have done. Then you can also define your local, your Dirichlet form. As soon as you've got your Dirichlet form, you will have your Laplace operator, and you can define the fractional Laplace operator as I have done. Then you need that the heat kernel is a sub-Gaussian. That this follows from your property. Okay, it's they check that for this kind of fields you have the sub-Gaussian estimates, and this kind of fields also satisfies what is called the midpoint property. As soon as you take x and y and in K, you can find some z between the two in some sense, such that the distance between x and z and between z and y is the distance between x and y, 1/2 of this distance. Okay? Okay, so that just means that you have other examples that works. And now, what is stable fractional random fields? So in fact, that's an ongoing work. So the paper is not yet finished. So I will only give you some results. I have no doubt about the result, but we have to finish the paper. So the difference there that will rely on W. In the first part, W was a Gaussian measure. Okay. Here, it won't be a Gaussian measure, it will be a stable random measure. And we take a symmetric stable random measure of order alpha. So I don't explain you what is a stable random measure. That's exactly the same definition as for Gaussian random measure, except that the last line was W of A is a Gaussian variable. There, the last line will be W of A is a stable variable. Okay? And if you take alpha equal to 2, you recover the Gaussian case. So what's happened is now the random field XS applied to F will be not anymore a Gaussian variable. It will be a symmetric stable random variable. So that means that its characteristic function is now given by this. So now its distribution is not anymore characterized by its variance. It's characterized by what is called the scale parameter, which is this norm of F in L alpha. It's not the norm, it's the norm to the power alpha. Okay? we tried to provide some unified proof in order to consider the Dirichlet and the Neumann-Laplacian operator in the same paper and not in two separate ones. And what you can prove is that, so I only assume that alpha is between 0 and 2 and not equal to 2. Alpha equal to 2 corresponds to fractional Gaussian fields. Okay? And the tools are already different. So to prove this, I don't use the same tools as the one we use for fractional Gaussian fields. Okay? And so here, if S is large enough, we can prove that XS still have a density with respect to mu, and this density still be the integral of the Riesz kernel with respect to this new alpha stable measure. Okay? So in the Neumann case, GS is the one I have given in the previous slide. If you deal with Dirichlet Laplacian, you need to change a little GS. Okay. And if S is less than this bond, there is no density. Okay. If you take alpha equal to 2, you recover exactly, I think that one dW is missing there. Okay, I think it should be alpha minus 1 dH divided by alpha dW, so that if you take alpha equal to 2, you recover the lower bound I have given for fractional Gaussian fields. Okay, so sorry for the mistake. And so what happened is the following. If S is less than this bound, there is no continuous path. In fact, X tilde the density as unbounded sample path almost surely. If S is bigger than this bound, you can prove that X tilde has a smooth sample path, and you can obtain an upper bound for its modulus of continuity, and so the exponent will be given by this. Okay. So at the beginning, I was quite surprised. Why is there unbounded sample path? So in fact, to understand that it is not surprising, we have a look on what happened in the Euclidean case. What is the analog of the fractional stable fields in the Euclidean case? And in fact, you obtain what is called in the literature moving average fractional stable motion. You don't recover harmonizable stable fractional motion. You don't recover harmonizable fractional stable motion. You recover moving average 1. And for moving average 1, in the Euclidean case, it is already well known that for most of the the parameters, the sample paths are unbounded. Okay. Here, we've got exactly the same as what happened for Euclidean case. I see Antoine doing that. I think he isn't convinced. And so that's all for my talk. Thank you for your attention. When you will have the slide, you can find a short bibliography there. And so thank you.
Are there any questions?
I see how to construct a random Gaussian measure, but in the last part we talk about the W alpha stable. How to construct this W alpha?
W alpha?
Excuse me, could you repeat the question, because it's registered and it's difficult to...
Okay, if I have well here, because I think I need to go to see the doctor. You asked me how do I define W alpha? Okay, so W alpha, I don't know, it won't really maybe answer because I won't explain you the construction, but the difference is that, okay, I just So you can also ask does there exist some measure that satisfies this? The answer is yes, of course. And so what you will keep if you want to define W alpha, this property still be satisfied, okay? So you replace W by W alpha. This one is also fulfilled, okay? Satisfied, and so I need to change this, okay? And so now, how do I replace this? I just ask that W alpha of A is a symmetric alpha stable random variable with scale parameter mu of A. So that means that if you have a look on the characteristic function of W alpha applied to A, okay, it will be equal to the exponential of minus the modulus of U to the power alpha mu of A. Okay. So the difference is that with Gaussian 1, Gaussian will correspond to alpha equal to 2. Okay. Did I answer your question?
No, this is just one variable. And in the Gaussian measure case, we have the isometry.
Oh, okay.
You realize your measure. So in this case, do you have some isometry?
No, there is no isometry.
But you need something.
No, I don't need isometry. What I need is just this. I just need this. Okay. In fact, there is you can prove that so if you want to build it, you can first define for f, which is an indicator. Then you take the linear combination, and then you prove that there is a convergence in probability, for example, and you define W alpha applied to f as the limit in probability of the linear combination of W alpha applied to the indicator.
And this is not your definition of XS. This is the property of your process.
No, but this follows from the fact that what we know for alpha stable. So the reference for this, if you want, you can have a look in the book of Taku and Samorodinsky. And they do. You can find the construction there. Okay. And in fact, for W alpha, they build a stochastic integral. Okay.
I understand. No, thank you.
Not sure.
Are there any more questions? Or the question at the back with the speech presentation?
Thank you, Valerie. If the time allow me, I have 2 questions.
2. Wow.
2 questions to you. 2 because I like very much.
Thank you.
So my first question is a naive one. You introduce your object by saying that your object is a fractional primitive or a fractional derivative of a white noise. But can we apply, if we follow this point of view and we try to extend it, can we apply to your fractional process that says that its first parameter is 1/3? Can we apply to it the fractional Laplace operator of order, say, a half, and then can we say that we obtain another fractional process? Is there relations like that?
I don't know.
Even
I will say it's a good question, but I don't know. We didn't have a look on what happened if we apply the Laplace operator, the fractional Laplace operator to the field.
My second question is related with you want to find, you said that you have not succeeded to find an upper bound for the regularity of sample passes because you wanted to bound the...
I say that one way to obtain the optimality is try to obtain a lower bound for the variance of the increment. That's one way.
Yes, but this is one way.
Yeah.
There are other ways.
But I didn't succeed with other way, I know. I know that maybe I can also use self-similarity, but there, self-similarity, I didn't explain it. It's not exactly the classical one, and so I didn't succeed to use it in order to prove that h is the critical exponent. And then, in fact, we would like to do other thing with this field, and we would like to study, for example, some Hausdorff dimension of images, or even inverse images or images of random set, and we will need the lower bound to apply some classical technique of non-local determinism. So that's a key point for us if we want to follow the study we want to do.
Thank you very much.
Are there any more questions?
Do the same methods.
It's recorded,
I don't
so
hear you.
So do the same methods work on other fractals where you can define a Laplace operator, such as post-critically finite fractals or the Sierpinski carpet?
The fractals for which it works are the Barlow one. We can also generalize to some general metric spaces, but we really need the tools I mentioned, the Halford regularity, the sub-Gaussian inequality, and like this. But we know how to do it on general metric spaces.
Okay, if there are no more